Okay, so I will continue with this, which is an infrastructure for performing DRAM tests. I think this was mentioned a few times in the lecture. So yeah, we published this in HPCA 2017, 1 year after the charge cache paper. Yeah, and here we basically develop an open source infrastructure which is FPGA based to perform tests to characterize DRAM cells, which means like what is the, let's say the error pattern that you observe if you reduce the latencies, but do not observe anything like charge cache, right? So you just reduce the latencies for the worst case, what will happen in that case, or if you extend the refresh period, so instead of refreshing at 64 milliseconds, what will happen if you refresh every 1 second, right? So answering this kind of questions, to answer this kind of questions, you need an infrastructure to test real DRAM chips. And this is basically what we do here with SoftMC, which stands for like software-based memory controller. Okay, so let's again start with a quick summary. So two critical problems of DRAM are reliability and performance. So this is also becoming increasingly more important by scaling down the technology nodes. So not very recent, but raw hammer bug or raw hammer problem was discovered, right? And it only affects DRAM chips manufactured with small technology nodes. So if you remember from like from previous lectures, it starts appearing after 2008 or something like that, or 2010. Yeah, so definitely something changed in the interaction between the cells by reducing the transistor sizes, capacitor sizes too much. So in order to like attack those problems, we need an infrastructure to characterize, analyze, and understand the DRAM cell behavior and potential other components inside the DRAM. So to this end, we design and implement SoftMC, which is an FPGA-based DRAM testing infrastructure. Yeah, so we designed a software-based infrastructure that is flexible and easy to use. So if you want to use, you do not necessarily need to write any hardware code, for example. So we have a bit file for an FPGA, which you can put into your FPGA and then develop different tests in software without changing anything. And this is available as an open source project. So in this paper, we implemented two use cases using SoftMC. The first one is a retention time distribution test, which is a well-known test that you do to see what is the retention time of the cells in the chip that you are testing. So we did that to validate the correctness of the infrastructure, right? So the goal here is to see similar results to those published in prior work. And so we also did an experiment to validate the assumptions in two mechanisms on latency reduction. And one of them is charge cache. So we'll look at like whether charge cache makes sense, or like are all assumptions that we made 1 year ago were correct. Yeah, and we expect SoftMC to enable a wide range of studies, and it's like already being used. So if you look at like papers from Professor Mutlu's group, you will see that there are like different DRAM characterization studies that look at like temperature variation, voltage variation, and like they use different versions of SoftMC to perform those tests. Okay, so since I just presented those DRAM basics and motivations in the previous slides, so I will go very quickly over those because there's slight differences that I want to emphasize. So again, so here we assume that we want to access this cell over here. So the same thing happens. We activate the row, charge flows to the sense amplifiers, and then sense amplifiers store the charge back, right? And then after this point, the memory controller can issue a read operation, and then the data is transferred, and then we pre-charge in order to be able to access another row from the same bank. Yeah, so basically those are three main operations that DRAM performs. So yeah, and in this slide, I would like to show what happens to a DRAM cell during those operations. So first, when a DRAM cell is not activated, so it's like in a pre-charge row, what happens is it leaks charge over time, and at each 64 milliseconds or 32 milliseconds, the memory controller is issuing refresh commands to restore it back so we don't lose any data. So we define the time interval during which the data can be retained correctly in a DRAM cell as a retention time. And so here in this case, it seems like the retention time of this cell is 64 milliseconds, right? But it doesn't have to be. So we kind of have a guard band over there. So, I mean, so maybe most of the cells in a DRAM chip can retain data for much longer than 64 milliseconds, right? But we still refresh at 64 milliseconds to ensure that everything goes well under different conditions. Okay, so when we activate, after this ready-to-access latency, where the memory controller can issue a read operation, this is what happens to a DRAM cell and sense amplifiers over here. Right? So it is like not fully charged, but they all contain some amount of charge that can correctly drive the rest of the circuitry, so we can read and write data to the sense amplifier. And then after this activation latency, we can pre-charge, which just closes the row. And at this point, we have both cell and sense amplifier fully charged. After this pre-charge operation, which is basically putting the sense amplifier and the bit lines to their pre-charge level voltage, which is like half VDD, right? So it's like between VDD and 0. Then we can issue another activate to another row. And this latency here is defined as pre-charge latency. So in this slide, let's look at what will happen if the memory controller decides to reduce those latencies to improve performance. So if you move this read command over here, what will happen is the charge level here on the sense amplifier will be lower than here in this point, right? And this may potentially result in reading incorrect data because the sense amplifier here is not ready to read voltage level. So if you issue the pre-charge sooner, what will happen is we will close a row when the cell is not fully restored, right? So if you don't access this cell again within 64 milliseconds, since it's not fully restored here when we pre-charge, it may also get its data corrupted at the end of 64 milliseconds, right? Because it will leak this charge and it will go below the threshold for whatever data it's storing. And so similarly for pre-charge latency, so if we, after issuing a pre-charge, if we issue an activate command sooner, then basically we will try to activate a row when the bit lines are not in half VDD, right? And this will basically work against the charge stored in the DRAM cell. And again, this may result in data corruption. Okay, so basically violating these latencies negatively affects DRAM reliability. So it doesn't mean that you'll always get an error, but it just increases the probability of getting an error if you play with those. So other factors affecting reliability and latency are temperature. So if you increase the temperature, cells leak more charge. Similar observations for voltage. So if you play with voltage, it changes the cell leakage characteristics, and also it changes the characteristics of like charge movement. So it also affects your reliability. Intercell interference is another factor, and here basically we see this in the row hammer effect, right? Because of the interference between cells, we we see that row hammer problem where like continuously activating a single row causes bit flips in rows in the neighborhood. And yes, another factor is manufacturing process. And this is basically due to imperfection in the manufacturing process, right? So not all the DRAM chips that you manufacture are like perfect. Some of the cells are smaller, they like leak more charged. And yeah, the sense amplifiers also have some structural variation. And retention time is also another factor. So different cells have different retention times for different reasons. And basically, we need to develop mechanisms to improve those reliabilities, to improve reliability and latency. But to do that, first we need to understand what are exactly those, right? To understand how, to understand what are the error patterns, for example, while playing with those factors. So yeah, there are many factors, as I showed, that affect reliability and latency, and those are not easy to model in simulation or analytically. So we really need to perform experimental studies on real DRAM chips to understand those problems. And then maybe we can develop some simulation-based models after understanding. And to do that, we develop SoftMC. So before showing what is SoftMC and how it works, I would like to go through the goals that we think a DRAM testing infrastructure should achieve. So the first goal is flexibility, and this is basically the ability to test any DRAM operation at any order with like any timing parameters in between them, right? So we should be able to precisely set a timing parameter between activate and read, for example, or other commands. Okay, and so here by any DRAM operation, I mean all the command that a DRAM specification supports. So if you open a DRAM datasheet, you will see a truth table with the commands supported. Yeah, and those are, so some of them are, as I mentioned, like activate, precharge, read, write, refresh. So another goal that this infrastructure should achieve is ease of use, right? So it should be very simple to program. It should require minimal effort, because your goal is not really, it shouldn't be always developing such an infrastructure, right? So your goal is to test the DRAM and understand how it works or how it reacts to changes in different operating conditions. And so by providing ease of use, it will be accessible to a wide range of users, even people who like experiencing hardware design, right? So you may not know how to write a code for FPGA, you may not know how to program an FPGA, but you will still be able to run some DRAM experiments if it just provides you a, let's say, C++ based interface or any other programming interface in any other language. So here we have a picture of one of our setups. And okay, so here what we have is basically the FPGA, which runs the hardware part of SoftMC, and we have the DRAM attached to it. So this is the DRAM that we test, right? And then we have the host machine here, which is connected to the FPGA over the PCI Express bus. And the host machine is sending instructions to the FPGA to start the test, to perform different kinds of tests, right? So you develop your test here, which I will show in the next couple of slides. And to ensure that we are operating at stable temperature during the experiments, we have a temperature controller and heater here. So yeah, and heater and also the DRAM over here is inside the heat chamber. So this is required because if we just let it run on a room temperature, which may be different during different times and during and because of like operations you perform on DRAM, right? So it will heat up by itself if you access it more. So this will change the results that we get, because reliability also depends on temperature, right? So if you want to analyze, let's say, the effect of reducing timing parameters, you have to be sure that you're running at constant temperature. If you cannot achieve that, you don't know basically if the errors you get are due to increasing temperature or reducing the timing parameters. And every time you will get maybe random results because of fluctuation in the temperature. Okay, and this is the FPGA that we use from Xilinx. And yes, we also develop a C++ API. So those are the three main components of SoftMC. So we have this API that is used to develop DRAM tests. And then we have a PCI Express driver and also a hardware component that is basically all the logic behind this API that runs on the FPGA. Okay, so let's start with the SoftMC API. So here so I won't go into too much detail, but I just want to show this simple example where we write a single cache line or a single chunk of data to DRAM. So those are the function calls we need to make for that. So how SoftMC works is it expects a structure called instruction sequence from your host machine, right? And then, so basically we here create this instruction sequence. We insert a bunch of commands into it and then run this execute function to send these commands to the FPGA, and the FPGA is executing those in order. So let's go quickly over those instructions. So we call those those functions instruction generator functions, and basically those directly corresponds to the DRAM command that you have that your DRAM chip supports, right? So for example, here we see the activate, which takes the bank ID and row ID as a parameter, and you can basically using this function call, you can tell SoftMC hardware to activate, let's say, bank 0, row 0, or some other row in some other bank. And so since we also want to have precise timing between like different commands, we also have here a function that generates a wait instruction. So this is like a bunch of back-to-back knobs that you know from like other instruction set architectures, right? So here this is set to some value of TRCD. Right, so this way we ensure that after issuing this activate command, SoftMC will wait for that many cycles before issuing write. So basically using this, you can set this to something very small and see what happens, right? So this is something you cannot do with your desktop machines. So some like laptops or like desktop machines provide you some control. So if you go to BIOS settings, you can play with those parameters a little bit, but it's not as flexible, right? And you cannot do it in per access manner. So you have to set it like during boot time, and it's fixed. So it's not like a very good platform to run this kind of tests. Yeah, and similarly, we have some other functions here, and this last function basically indicates that this is the end of the instruction sequence. And then once you create this, you can potentially reuse it multiple times to repeatedly perform DRAM accesses. Okay, I guess I had some animations over here. Okay, so the next component is PCIe Drivers. I won't go into too much details, but here we basically use a open source IP core called Rifa. Yeah, which is available on GitHub. I don't have the link here. And we basically modified it to be an interface between the host machine and SoftMC hardware. Okay, so let's take a look at the details of SoftMC hardware. But before that, do you have any questions like regarding this like programming thing or anything else? Yes.
Does it have support for loops?
No, not actually, not in this version. Yeah, so you cannot do that, but you can form loops in software, right? So you can basically have, you can send this instruction sequence multiple times from software, so you can achieve pretty much the same thing. Yeah. Okay, any other questions? Okay, I guess I will finish this, and then after finishing this, we can have a break. Okay, so here we have the host machine. So here in this slide, I will show you what we have implemented in the FPGA, right, as a hardware part of SoftMC, which is called like SoftMC hardware over here. So this big box here is the FPGA, and here we have DRAM, which is connected to the FPGA, and we have our host machine, which has its own DRAM, but we are not using it to test. So we have the PCIe Express controller here, which communicates with the host machine. And we have some other bunch of structures here. So one of them is instruction receiver, which is basically getting some data from this PCIe controller and puts that data into an instruction queue. And this basically buffers the instructions received from the host machine. So those are instructions that will be executed. We cannot start executing instructions right away. We have to buffer them to avoid PCI Express latencies, right? So assume that we executed an instruction right away after receiving it from the FPGA, from the PCI Express. Since we don't know exactly when the next instruction will come in from the PCI Express, it will be, we can't ensure precise timing between the commands, right? So we need to buffer them first, and then start executing them once we get the entire instruction sequence. Yes, and this is basically some circuitry that dispatches those instructions to DDR5, which is an integrated block in the FPGA that can communicate with the DRAM at high speed. I think I had animations here. Okay, so the host machine here sends some instructions to instruction receiver, right? And these are buffered, as I said. And then after all instructions are received, this instruction dispatcher executes them one by one. So here in this example, the first command is activate, which tells the DDR5 to issue an activate to the DRAM, right? So the next instruction is wait. So this is to implement TRCD, right? The latency between activate and read. So this is not producing any DDR commands over here because it's just wait. It's not doing anything to the DRAM. And the last instruction is read, which again generates a read command, and this goes all the way to the DRAM, and DRAM returns data back, which is captured over here and sent back to the host machine. And in the host machine, we can look at this data and see whether we have any errors or not. So we are not processing the data that we read from the DRAM on the FPGA, because we can do it in a much more flexible way in the host machine. And we have also some other components which deal with auto-refresh mechanism and some collaboration on the DDR bus to ensure data integrity. Okay, so let me quickly go through these two use cases. So the first use case is, as I said, retention time distribution study, which we do only to show the correctness of the implementation of SoftMC. Right? And so here I will show you how to implement this using SoftMC. So basically, first we start with writing some reference data to a DRAM row, and you can do it using like this piece of code over here, which is about 12 lines. And then we wait for some refresh interval after writing, so cells can leak their charge, and then we read back and check for errors. And so basically what we do during this test is we sweep this refresh interval and look at like how the fraction of errors change during the test. And this entire thing can be implemented with about 100 lines of C++ code. Yes?
How did you ensure like accurate timing? Like the host piece is probably on the links, or the real-time links or anything?
So are you asking about this timing here?
Yeah.
So for this one, we just use, I think some, what is it called? I think sleep instructions, sleep functions from the, like whatever operating system provides. So we don't have to be too accurate here because the refresh interval is something large, right? So it's in like order of milliseconds in the best case, but usually we are testing much higher. We are testing in order of seconds. Because at 64 milliseconds at room temperature, you don't see any errors. Like even at 128, it's very unlikely to see errors. at room temperature. Yes, but for the timings between commands, I showed that in the previous slide, right? So we use a wait instruction to ensure precise timing over there because that's important. That's just a few cycles of latency, and we have to be very precise over there. Okay, and those are the results that we get, and those basically. So here we show number of bytes that have at least one error for 3 different modules, and I think those are averages across like multiple modules from each vendor. So here A, B, C are different DRAM vendors. And yeah, we find that those results match results previously reported by prior work. Yeah, so basically this experiment validates the correctness of our implementation. And let's go to the second use case. So in this use case, we look at those 2 ideas proposed in this, I think it stands for non-uniform access time memory controller, and charge cache, which I presented a couple of minutes ago. And so the key idea of this mechanism is basically to access highly charged rows with low latency, right? So here we looked at using SoftMC, whether it's really possible on current devices. And here, this basically shows the idea of the mechanism. I will skip this. We already know all of this. So this is the way we implemented the test using SoftMC. So again, similar to the other test, we start with writing some reference data to the DRAM and then wait for some wait interval or refresh interval, and this is basically to let the cells to leak some charge, right? So here we basically sweep the amount of charge stored in the DRAM cells. If we wait for a lot of time, what will happen is the cells will contain smaller amount of charge. If we wait less, they will be highly charged, right? So we sweep this to see what will happen when we read back the data by sweeping the ready-to-access latency parameter TRCD. So here I think we sweep it from 11 to 6 or something. And yeah, we basically observe errors after reading back the data with different TRCD. And we repeat the same experiment with different wait intervals to see what happens when cells are at different charge levels. And this again can be implemented with 150 lines of code approximately. So this should be how the results should look like when we perform this test. So this is not real data. So those are expected curves for different latencies of TRCD. So here each curve basically corresponds to a different TRCD latency over here, which is the latency between activate and read operation, right? And on the y-axis, we see the number of errors. Yeah, so what should happen is, so let's say at this point, while it is safe, maybe at this point over here somewhere, while it is safe to read back the data with high TRCD, with 6, at this refresh interval, we get errors when we reduce the TRCD, right? And this is basically the case where the cells are not highly charged, right? But when they are highly charged, it should be possible to correctly read it with 6 and also lower latency. So I think here we, in this chart, we show that we start getting errors with 3, but we don't get errors with 4 and 5 cycles of latency. So this is what should happen. And this is the real data that we get. So yeah, as we see here, those 2 lines, which corresponds to, I think there are 3 lines actually, 6, 5, and 4 cycles of latency, they kind of overlap with each other. So if we zoom in a little bit, we see some, I think 4 is getting slightly higher number of errors in like some samples over here, but it's not like consistent, right? So it's not as nice as this curve over here. Yeah, so something is not working as expected, right? And we looked at what is the reason for this. And yeah, just Yeah, and for the 3 cycles of latency, we get a lot of errors, even when rate interval, when refresh rate is very low. And this is basically because we get errors due to something else, but not because of the charge level of the cells, right? So it basically cannot be performed, the read operation cannot be performed at this level, even when the cells are very highly charged. Yeah, so we don't observe the expected latency reduction effects of those previously proposed mechanisms. And here again, I think this just, okay, I think I will go through this. So this is similar to what I showed previously in other slides. So this is chart basically shows what will happen to those voltage levels of the cells and the sense amplifier while we are issuing those activate and read commands. And so we found that we cannot externally control the time when a sense amplifier gets enabled. So this is something I skipped in the previous slide, so let me explain it here. So when we activate a cell, so it shares charge with the sense amplifier, right? So they meet at some point over here. So after this point, the sense amplifier gets enabled and senses the value and starts restoring the cell back to its original value, right? So it happens here at this point. And we found that actually we don't have control over this, so we can't play with this. So reducing TRCD doesn't help with reducing this latency over here. Because TRCD is this point, right? So it is something that the memory controller needs to obey in order to ensure the correct access, but it's not really changing any internal timing in DRAM. So it's not causing the sense amplifier to be activated sooner. But the sense amplifier is always activated at this point of time, right? So it's some fixed latency after activate command. So when we access a highly charged row, what we really want to do is to move this point over here where the sense amplifier is activated here, so we can get this reduction. So if we can't do that, we don't get significant benefits over here because we waste a lot of time here waiting for charge sharing, but charge sharing has already completed, right? So it's at a sufficient level to read the data back. Okay, so yeah, this is the main problem why we didn't observe the expected latency reduction benefit. So there are some future research directions that SoftMC can enable, and you can basically perform more characterization studies of DRAM. So it's possible to look at how are the cell characteristics changing with different generations of technology nodes. Right? So 2 years later, you can look at what will happen to DDR5. For example, when the technology node scales even further. And it's also possible to look at what type of usage accelerates aging. So we know that electrical components are showing some problems when they're aged, right? So yeah, potentially someone can develop a mechanism to quickly age a DRAM chip and then look at the error characteristics. So by extending SoftMC, it should be also possible to experiment with non-volatile memories. And some other extensions could be implementing some logic to support memory scheduling, different memory scheduling algorithms, and develop a test bed for workload analysis and in-memory computation. Again, those requires extensions to SoftMC. You cannot just do it by writing some code in software. You need to modify the Verilog code on the FPGA. Okay, and as a conclusion, SoftMC is the first publicly available FPGA-based DRAM testing infrastructure. And it is flexible and easy to use. You can issue any DRAM commands to the DRAM with precise timing. And we showed 2 different use cases for it, right? So the first one was to show the correctness of it, and the second was looking at whether the assumptions of 2 previously proposed ideas were correct. And SoftMC, we believe that SoftMC can enable many other studies, ideas, and methodologies for designing future memories and memory controllers or memory systems in general. And yeah, our prototype is available on GitHub over here. this link. Yes, I think that's it. Do you have any questions? Yep.
So do you like circumvent the existing memory controller on the DIMM chips?
So we only use that DDR5 logic block, which is like hard IP block on the FPGA, right? And we kind of have to use that because otherwise you cannot communicate with the DRAM interface at very high speed. So it's not like a regular I/O that you can do at very low speed, right? So that like the interface has some like specific electrical specification, and you need to meet that, and it's not easy to do with configurable FPGA logic. So this is why FPGA manufacturers put those hard IP blocks. And what we are using is basically that. Other than Phi, we don't use anything else. Yeah. Okay, if there are not any questions, I think we can have a 10-minute break. Okay, and I guess we can start in 10 minutes.